So the problem is the 2 raised to n vertices of a graph G correspond to all subsets of a set of size n, and n is greater than or equal to 6. 2 vertices of G are adjacent if and only if the corresponding sets intersect in exactly 2 elements. And then there are these 3 questions which are somehow connected to this thing that is given to us, and we have to answer these 3 questions with their corresponding options A, B, C, D, and A, B, C, D. Okay, so what is given to us is that there are 2 raised to n vertices in a graph G, okay, and these vertices correspond to all subsets of a set of size n. Alright, so if you have a set of size n, that's what is mentioned, then you can have 2 raised to n subsets. This thing you must know by this time, that this is from your counting class, that how many subsets can a set of size n have. It's 2 raised to n. Okay, and then these subsets are represented by vertices. These 2 raised to n subsets are represented by vertices of this graph G, and in this graph 2 vertices are adjacent if and only if the corresponding sets intersect in exactly 2 vertices, 2 elements. So you have a graph with 2 raised to n vertices, and when do you have an edge between 2 vertices? If the sets that those 2 vertices represent have exactly 2 elements in common. Okay, it's exactly 2 elements. And then we have to answer this question: the number of vertices of degree 0 in G is, and these are the options. Okay, so what is asked is how many vertices are there of degree 0. So what does degree 0 means? Degree 0 means that the vertex is not, so I'll write question 1. The degree 0 means that a vertex will have degree 0 when it is not connected to any other vertex. Okay, that is degree 0, which is fine. And if it is not connected, what does that mean? That it cannot have 2 elements in common with any other set. Okay, so out of these 2 raised to n subsets that you can have, you have to find all those subsets which cannot have 2 elements in common with any other set. So what are those subsets can possibly be? Okay, so let's first talk about the empty set phi. This is the empty set phi. Okay, so this set doesn't have anything, so it cannot possibly have 2 elements common with any other set. So this must be included in our answer. Okay, and what else? What about the sets with just one element? Sets with just one element. So what can we say about these sets? Like sets of the type, suppose I I say that the elements of this set of size n are, suppose I say that the elements of this set of size n are 1, 2, 3 and so on up till n. Suppose this is what I have assumed that these are the elements of set. By, like, without any loss of generality, I can say that these are the elements of the set. And what are these sets? These are subsets 1, 2 and 3 and so on up till n. What are these? These are the subsets with just one element. Okay, and since they have only one element, they cannot possibly have what? Exactly 2 elements common with some other subset. So all these must be included in our answer to the question number 1. What about anything else? Can we have anything else? All the other sets will have at least 2 elements, and if we have at least 2 elements in a set, we can always find another set which will have two elements in common with that set. Okay, you take any element with you take any set with number of elements greater than or equal to 2. Okay, and you can always come up with some other subset that will have at least two elements common with that one. Okay, so this is 1 and this corresponds to n. These, if you count these subsets, these are n, so this becomes n plus 1. Okay, so that is option C. Oh, that is fine. Okay, good enough. So this solves the question number 1. Alright, so now we'll come to question number 2, which is a bit trickier and is, you can say, more involved. So what about question number 2? The maximum degree of a vertex in G. Okay, so which vertex in G can have a maximum degree? So what we will do, we'll see one by one. We'll talk about the vertices that have degree, that have only two elements in the subset. We will talk about the vertices that have only three elements in the subset. Okay, because you have all the subsets, and we'll see in which case we get the maximum degree. So the first thing I will do is we will talk about sets with only two elements. Okay, so without any loss of generality, I can talk about this set 1 2. I can talk about any other set also. I can talk about a set 1 3. I can talk about a set 1 4, or I can talk about a set 3 4. They all will have same degree, because in a set the elements, the ordering of the elements don't matter basically, and we have only one condition out here, that the edge exists when they have exactly two elements in common. So without loss of generality, I can what I can do is I can take this as my set with only two elements. What will be the degree of the vertex that will correspond to this set? To which all other vertices will this vertex have an edge? So let's start with the biggest one. Okay, so let's talk about this one. The biggest subset that you can have is this one. Okay, so there will obviously be an edge between these two, right? If I'll make this one like this, there will be an edge between these two, because they have these two elements in common, 1 and 2. Okay, what about this one? What about if I come up with 1 2, and in the rest of the places what I have done is, out here I have n elements, so this one was with n elements, and now I have to choose with n minus 1 elements. Okay, so what can I do in this case? So this is basically, you have to fill these places. Okay, but there should be in total only n minus 1 elements. So when I have chosen 1 2, because I have to keep 1 and 2, because I want to have an edge between these two. What I want is, I want to have an edge between these two, so I have to keep 1 2, and the rest I can choose freely. Okay, so if I choose the rest freely, but I have to have a total of n minus 1 elements out here. So what I can do is, out of the n minus 2 that were left, I can say that, okay, I will include everything out of these n minus 2, but not one element, because that is the one I will exclude. So I will have in total n minus 1 elements. So this can be done is n minus 2 C1 ways, and this is only one way, and you can see that this can also be done in n minus 2 C0 ways. Okay, because you are not excluding anything. See, out of these n minus 2, you are not excluding anything, you're including everything. Okay, in this case you are excluding one, and so on. You can go ahead. Okay, what you can do is, you can have another set. Okay, 1 2, and these you have to choose, and in this case what you have to do, in total you have to have n minus 2 elements. So out of the remaining n minus 2, Okay, what you have to do, you have to exclude two elements. So this you can do in these many ways, and you can go on this, you can go on. And when will you end? You will end when you will have 1 and 2, and you have to choose only one more. Okay, you have to put one more element here. All right, so in that case, what you can do is you can select this element out of these n minus 2 elements. Or what you can do, you can, out of these n minus 2 elements, what you can do, you can exclude, what, you can exclude n minus 3 elements. Okay, and then you can sum up all of this. So when you do this summation of all of these, you will get the degree of this one. You will get the degree of this 1 comma 2. So what will be the degree of this one when you add all these? So this shouldn't be difficult to you because it's from your counting class again, and they should give you a value of 2 raised to n minus 2 minus 1. So this is the degree of any vertex that corresponds to a subset with two elements. Okay, that is fine. You just add these, and this is a simple formula that you have for these additions. Okay, n minus 2c0 plus n minus 2c1 up to so on n minus 2c n minus 3, just one less than n minus 2 is out here. And in that case, this is the formula you get by adding all of these. So we'll keep it in our mind, and we'll just keep it here like this: 2 raised to n minus 2 minus 1. And this is the case with when you have two elements. Okay, so I'm writing it on the side so that I don't forget it, because I'm going to change everything out here. Because now what we are going to do is we are going to talk about the sets that have only the sets that have three elements. We're going to talk about such sets, and again, without any loss of generality, in the same manner I did before, what I can do is I can select 1, 2 and 3. This is what I can do. All right, and again, so what I have to do is I have to find the other subsets with which this one will have edge, with which this one will have an edge in common. Okay, so and when will I have an edge in common? When I have two vertices in common. Okay, exactly two elements in common. So this vertex, this vertex which corresponds to this subset 1 2 3 will have exactly will have an edge with those vertices with which it will have exactly two elements in common, and those two elements can be 1 2 or 2 3, or they can be 1 3. All right, so basically if you have to select those elements which you want to be in common, then you can do that in 3c two ways. Okay, you can select 1 2 or 2 3 or 1 3, and then again you can do the same sort of thing. Okay, you can start with 1 2. All right, you can start with 1 2, and or you can start with 1 3, or you can start with 2 3. Okay, and you have to fill this, you have to fill this out. Okay, so what I'm going to do is I have to find those sets with which it will be common. So I shouldn't put this closing braces out there. So what I have to do in this case is I have to fill the rest of the places. Okay, and what I cannot do is, in this case I cannot choose from the 3. Okay, so 1 and 2 are gone, 3 is also gone, because I need exactly two elements in common, which are 1 and 2. So basically I have to choose from n minus 3 elements, and that can be done in n minus 3, or I have to exclude nothing. I can say n minus 3 is 0, c0 ways. Okay, and the same can happen with all of these 3. So this complete argument becomes 3c2 into n minus 3 c0. Okay, and this was this was for n minus 1 elements. Okay, and then you can do this for n minus 2 elements, and then what you will get is 3c2. Okay, and then you have to do what? You have to choose in total there should be n minus 1 elements. Okay, so you have to choose from n minus 3, but then you have to exclude only one element, and this can go on, and ultimately if you will try to find the total sum of these all, you want to sum up all of them. So what you will get is 3c2 into, and in this case when will you end? In this case what is interesting is you can end at something like this. Okay, I'll talk about this one. You can end at something like 1 2, and then you have to choose something out here. Okay, you have to choose something out here which cannot be 3, but it can be everything else. So from these n minus 3 you don't have to exclude anything. So if you do the sum, this whole thing will go on up till 3c2 into n minus 3 cn minus 3. Okay, like this. So this will give you 2 raised to what? This will give you 2 raised to n minus 3. That's what this is going to give you. Okay, so I'm going to write this also. Okay, out here with my 3c2 into 2 raised to n minus 3, and I have to correct this one a little bit. Okay, so n minus 3. Alright, so this one is for how many elements when the set has 3 elements. Alright, and then what I can do is I can do the same thing. Okay, I can do the same thing, but this time what I can do is I can have, instead of 3, I can have 4 elements. Okay, so this is what I can do next time. I can have 4 elements like this, and you can do the same argument, everything will be same, and finally the sum that you're going to get is 4c2. Okay, because you have to choose 2 elements, okay, that you will have to find in common, into 2 raised to n minus 4. Okay, so this is the sort of thing you are going to get. So okay, I'm going to write it again here. So 4c2 into 2 raised to n minus 4, and this is for 4 elements, and for the rest of it, as you keep on increasing these elements for different vertices, you will get this sort of thing. Alright, so let's see what you have got here. Which thing is bigger out of all these? So let's first compare these two, this one and this one. So what do we have? We have 3c2 into 2 raised to n minus 3, and what I can do is I can write this as 3 into 2 raised to n minus 3, and what I will do is I'll write it 1 plus 2. Instead of 3, I'm going to write 1 plus 2 into 2 raised to n minus 3, and when I open up the brackets, what I'm going to get is 2n minus 3 plus this 2 times this will be 2 raised to n minus 2. Now what you can do is you can make a comparison. You can compare this whole thing with this one with 2 elements. So this is 2 raised to n minus 2 plus something. Okay, and this is 2 raised to n minus 2 minus something. So this one is obviously smaller. So this one you can say that this is definitely not maximum. This is, you can say. And then what we are going to do is we are going to compare this with the the case when we have 4 elements. And what is that case? Let's see what is that case. Okay, so the 4 element case is this one. So okay, this one, if you take, what do you get? You get 4c2. 4c2 is 6 into 2 raised to n minus 4. Okay, and then what you can do is you can write this as 2 into 3, or 3 into 2 into 2 raised to n minus 4 is equal to 3 into 2 raised to n minus 3. So this and this are basically same. Okay, so both are equal. This with the degree of the vertices with 3 elements and the degree of vertices with 4 elements is the same, because we're getting the same expression. All right, and if you go higher, what happens if you go higher? Okay, let's take another thing. Let's take the case when you have 5. So when you will have 5 elements, what sort of expression will you get? You will get something like 5 5c2 into 2 raised to n minus 5. So this is what 5c2 is 10, and 10 is nothing but 2.5 into 4 is 10, that is 5c2 into 2 raised to n minus 5. So what you get from this is 2.5 into, this is 2 raised to 2, so this becomes 2 raised to n minus 3. Alright, because you can write it 2 raised to 2 and this can go here. Now if you compare these two, okay, just compare these two. This is 3 into 2 raised to n minus 3, and this is 2.5 into 2 raised to n minus 3, so obviously this thing is bigger. So with 5 you get smaller, and with 3 and 4 you get equal. And let's nail it down finally. So what you can finally do is that you can look at the sort of expression you get for 3 and greater. What sort of expression do you get? You get something like this: kc2, and sorry, you get something like kc2 into 2 raised to n minus k. Okay, and what I can write this is kc2 is nothing but k into k minus 1 by 2, and I can write these separately: 2 raised to minus k into 2 raised to n. So what this is like exponential thing. Okay, this will go in the denominator. Okay, it becomes 2 raised to k. So when you will increase k, as we did from 4 to 5, what happens is that this exponential term will dominate, and since this goes into denominator, the value will keep on decreasing. So as you keep on increasing k, you go from 5 to 6 to 7, you are not going to get greater degrees. Okay, you are going to get smaller degrees, because this is an exponential term and it goes into denominator. 2 raised to k goes into the denominator. Okay, this is k, and then as you keep on increasing, it will decrease the whole term. So you're not going to get bigger than this if you increase your k. And so this kind of leaves you with this thing. Okay, this is the same thing as this which we got for 3, because 3c2 is 3 into 2 raised to n minus 3, which is option 3. So that is our option. I know it's longer, it's involved, it's takes time, but that's what we had to do to solve this one. And then we come to the third part, question part 3. And the part 3 is quite simpler, it's quite easier, because In this case, you have to tell the number of connected components. So it's related to this part 1. In part 1, what did you do? You found these isolated vertices, okay, degree of 0, 1. So how many were there? There were n plus 1 isolated, okay, they were isolated vertices. So they are components in themselves, n plus 1, okay. And what about the rest? About the rest, okay, you can always have and you can always find some connection from one to the other, okay, because you can always find at least two elements common in the rest of those, okay. So they don't, they sort of connect with each other, and so they form one component, they form one another component, and you had n plus 1 earlier and these 1, so which gives you n plus 2 as the total number of components. All right, so that's it.